Welcome back, everybody. Section 1.6 is all about graphing functions. Now, in Chapter 1 so far, we've talked about a few topics that could help you with your graphing, or just make sure that your graph is on target. One of the topics we've talked about so far is symmetry. The second one, which is important, is our table of values. And the third one, which we discussed before, is slope. We've talked about other things that also could help with graphing, but these are the three major topics that could really help you either make your graph or double check to make sure that your graph is on target. Let's review for just a second. All right, let's take symmetry. And I'm not going to go through symmetry all again. If you want to, you're certainly welcome to go back and check out the past video. But I do want to talk just quickly about odd and even functions. All right, and again, I talked about odd and even functions before. You are welcome to go back and check that out. Here's another slightly different way to check to see if you have an odd or an even function. So, say the function is even if f of, x equals f of negative x. All right. So let's take a function like x squared plus 1. A fairly basic function, and I'll tell you right now, it is even. All right. You wouldn't normally know that when you started, but I'm already telling you that this function needs to, right? We expect it to fit that rule because it is indeed an even function. So right now I have f of x, which is x squared plus 1. Now the question is, the review for a second is, what is f of negative x? Well, remember my x is kind of like a parenthesis, and inside that parenthesis, instead of having x in it, I'm going to have negative x in it. Squared plus 1. And let's simplify this, and we wind up with x squared plus 1. Therefore, the function is even. All right. Like I said, an example that you would have on any sort of an assessment would give you a function, say, is it even, is it odd, is it neither? And then you would have to run through this test to see if it was indeed even. All right. So this is, the function is even. Just make sure we write that though. It's clear. All right. So my second test, obviously, is going to be, right, the function is odd if. And the function is odd if f of negative x equals negative f of x. All right. So my example is going to be f of x equals x cubed. I'll make a better 3. I'll make a better x. X cubed. And again, this is indeed an odd function. Like I said, you wouldn't normally know that at the start. The question would be, is the function even, odd, or neither? Or test for symmetry. Now remember, a function is odd if it is symmetric about the origin. So if you answer yes to it is odd, you're also answering yes to is it symmetric about the origin. But let's fill out that statement and see if it's true. Like I said, our expectation is that it will be. So for f of negative x, so I have my parenthesis, I'm putting negative x inside the parenthesis, and cubed. and then I have negative, and then I just need f of x, which is x cubed. All right? So when I simplify this, I get negative x cubed equals negative x cubed. Hence, we have now confirmed that y equals x cubed, or f of x equals x cubed, is indeed an odd function. I typically use things like even and odd to kind of confirm that I'm going in the right direction. All right? I think it's really helpful for that. All right, the next thing we're going to talk about is increasing, decreasing, and constant. Now, people use these words all the time. Very often they lose their meaning just a little bit. So I do want to go over them just to make sure that we're all on the same page. All right, so let's start with decreasing. Now, there is a mathematical definition for decreasing, but when you have a graph kind of like this, basically what you can do is take a look if the function goes down like that, or the function goes down like this. You could comfortably say it is decreasing. All right? When you're talking about increasing, and we have a graph, if the function's going up, then it is increasing. All right? The last term we're going to discuss is something called constant. And if the function is staying the same, it is indeed constant. All right, so, but the question is, what do I do with a point like this? All right, you're not really going up at that point. You're not really going down at that point. All right, this point is called extrema. It's called relative extrema. Not really increasing at that point. I'm not really decreasing at that point. So that point is kind of like, there is a different name for it. And the general term is called relative extrema. In this case, this point would be a minimum, a low, right? A relative minimum. And we will talk more about that in just a second, all right? But I do want to talk about the intervals where this function is decreasing, all right? Now, when we talk about the intervals where it is decreasing, all right, we're talking about the x values. So I'm looking from this point to this point, it is decreasing. Now, I'm not including those points because those are my extrema. So I can say it's decreasing from -6 to -4, and it's also decreasing from that point to that point, so from 3 to 6. So when you're talking about the intervals where your function is decreasing, you want to use your x values number 1, you want to use your interval notation number 2. Okay? So let's talk about increasing now, all right? There's only one interval where it is increasing, and it starts at -4, and it ends at 0. All right, and again, the ends are not used, okay? So that's why we use parentheses. And for constant, we are constant from 0 to 3. All right? Do we have any questions about increasing, decreasing, constant? We can discuss it. Like I said, probably things that you've seen before, but it's one of those things that is definitely worth going over. All right, so now let's talk a little bit more about your local, that's a terrible L, local max, local min. All right, so anytime your function switches from increasing to decreasing, all right, So here is the exact point where it switches. It is called a local max. All right? The exact spot where it switches from increasing to decreasing. Just the same, the spot where it changes from decreasing to increasing, I'll use blue, there we go. That exact spot is called a local minimum. Now, the reason why we call them local is because every single time your function does this, you can have a local max or a local min. So technically, any function can have many local maxes, many local mins. All right? There is another term called absolute max, absolute min. All right? So we have absolute max, absolute min. All right. And if you wanted to look for an absolute maximum or absolute minimum, there can be only one. So if there is a point where the function is going to go no higher, right? Not only would it be a local maximum, but that one particular spot would be an absolute maximum. Just like if there was an exact point where the function could go no lower, you not only would have a local minimum at that spot, but it would also be considered an absolute minimum. Now remember, we're living in the real number world here. So things like infinity and negative infinity are not included in that. If the function goes to infinity, we're going to say for right now that we have no maximum. If the function goes to negative infinity, we're going to say that we have no minimum. Okay? So let's take a look. All right, here I have another graph. So I want to identify the local minima. All right, minima meaning plural of minimum. All right, and what we see here is, I'm going to use my highlighter, change the color to yellow so it gets a little brighter. All right, I have a local minimum here and I have a local minimum here because those are the two spots where it goes from decreasing to increasing, right? Decreasing to increasing. And at -1, +1, right, I have a local minimum. So, but we identify with the x value. So the local at x equals -1. And in this case, it would be at x equals 3. All right. Now, if they ask, what are the values of the local minimum? Right? So we're not asking where it is. What the location is the x value. The actual value is the y value. So the values would be 1 and 0. All right, are the y values. So there is a very subtle difference there. Now, 99.9% of the time, I want the location, which means I want the x values. Every once in a while, you might need to bring in the y value. So I just want to kind of try to make that distinction. All right, so I'm going to clear off a little space up here. And we're going to talk about local maximum. All right, so I'm going to change colors a little bit. So maximum is where I change from increasing to decreasing, and the exact spot where I change is that spot. So again, if I'm asking where is the local maximum, and listen to me clearly, where is the local maximum? The local maximum is at x equals 1. Remember, we're always using the x value for the location. The value of the local maximum at x equals 1 is 2. So in that case, we would use the y value. Now, is 1, 2 an absolute maximum? The answer is clearly no. On both sides, the function goes much, much higher. In this case, I would say there is no absolute maximum, but there is an absolute minimum. So Absolute minimum would be at x equals 3. All right. So now I want to talk a little bit about piecewise functions. Now, piecewise functions are kind of interesting. Typically, I find students have seen them before, but it's always good to go over. So a piecewise function kind of looks like this. I hate making those brackets. I can't make them right ever, but you kind of understand where I'm coming from. Negative x plus 1 if negative 1 less than or equal to x less than 1. 2 if x equals 1 and x squared if x is greater than 1. So basically what a piecewise function is a rule on a limited domain. Now this one has 3 different rules on 3 different limited domains. So if we're looking for values between 1 and negative 1, all right, we're going to use this rule. If we're looking for values when x equals 1, we're going to use this rule. And if we're looking for values when x is greater than 1, we're going to use that rule. All right? So here's what I'd like you to do. I'm going to say I want you to find f of 0, find f of 1, and find f of 2. So at this point, I want you to pause the video. I want you to take a moment, find all 3 of these. When you're ready, come on back. Great. All right, so for f of 0, I'm going to use rule number 1. 0 plus 1 is 1. For f of 1, I'm going to use rule number 2, right? So we only have 1 value there. And for f of 2, I'm going to use rule number 3, the last of the yellow rule, and that's 4. All right, so depending on what value you're looking for, you could be using a different rule. All right. Now, the second question I have with this is we need to graph the function. All right. So I'm going to scroll up. I'm going to say, so B is graph the function. All right. So what I want you to do is I want you to make 3 table of values. Now, there's a lot of different ways to graph. The one thing I like about the table of values is that students have a lot of experience with it, number 1. And number 2, it always works. Okay? So I want you to pause the video. You're going to make 3 table of values. Now, the reason we're making 3 is because we have 3 different rules here. Right? So this could be like table 1, table 2, table 3. And we can mark these table 1, table 2, table 3. And I want you to think about how you would set this up. All right? When you're ready, come on back and we'll talk about the answer. All right, so here's how I would set it up. Now, for the first rule, our lowest value is negative 1. Highest value is 1, but we don't quite get there. We get infinitely close. So I'm going to say negative 1, 0, 1. However, this particular value, we don't quite get there. So this should be on the graph as an open circle, this particular value. Now, the next table is pretty easy. There's only one point it could be, 1, 2. I'll make a better 2 for you. And the last table is greater than 1. So I have 1, 2, 3. Now, for that third rule, this particular value, like I said, it's not equal to, it's infinitely close. So just like before, open circle. All right. So if you haven't already done this, why don't you fill in this table of values? All right, and then it's just a matter of plotting the points. Now, the key with plotting the points is you do not connect the dots between the tables. Okay, now the two tables might overlap. That's okay. But if they don't and there's space in between, you do not connect those dots. All right, so pause the video now, fill in the table, and then why don't you sketch a graph and see where we're at. Okay, so for my table, I got 2, 1, 0, 1, 4, 9. All right, so once the tables are filled out, you can make your points, connect the dots. Like I said, do not connect the dots between the tables. So your graph should look something like this. Now, please note, all right, on this particular graph, I have a dotted line. This is what it would look like if we extended our domain. But so those dotted lines should, really shouldn't be there. But notice the open circles, closed circles where appropriate, and all 3 of my tables do not connect. I need to be very clear on that. All right, one more thing, and then we'll be done. The last thing is always a little bit of applications. This is, in particular, is an application for piecewise functions. In Peach County, Georgia, a section of interstate has a speed limit of 55 miles per hour. If you are caught going between 56 and 75 miles per hour, your fine is $50 plus $3 for every mile over 55 miles per hour. If you're caught going over 75 miles per hour, your fine is $150 plus $5 for every mile over 75 miles per hour. A is find a piecewise function that calculates your fine. And B is what is the fine for 60 miles per hour? What is the fine for 90 miles per hour? All right. So let's start with the piecewise function. All right. So usually what I like to do is I kind of like to highlight some relevant stuff. So I'm going to use my highlighter. All right, so speed limit is 55. I like that. If you're caught going between 56 and 75, $50 fine, $3 for every mile over 55. I'm going to change color. Still important, just different. Right, for every mile over 75, it's $150 plus $5 for every mile over 75. So this has a lot of good information in it. Let's try to sort it out. All right, so first I need my piecewise function. And I'm only going to have 2 rules this time because they only give me information for 2. Well, my fine for going over 55, right, between 56 and 75 is a $50 fine plus $3 for every mile over 55. So if I do x minus 55, let's say I was going 60. 60 minus 55 would be 5. 5 times 3 would add on to your fine. And that is if x is between 56 and 75. My second fine is $150 plus $5 for every mile over 75. $5 for every mile over 75. So I'm going to do x minus 75. And that's if x is greater than or equal to 75. This shouldn't have an or equal to over here. See if we can. Oh, there we go. Right, because once we get up to 75, we jump to the next higher rung of the ladder. All right. So now, really, for part B, I really just want to know what f of 60 is. I'm used to using lowercase letters, and this time I used uppercase. And f of 90. So why don't you pause the video real quick, run through the calculations, f of 60, then f of 90, and we'll talk about the answer on the back end. All right, for f of 60, I got 65 miles per hour, or $65, excuse me. And for f of 90, I got 225. All right. Now, to me, the labels are important. All right. We do a lot of math. We do a lot of graphing. We do a lot of concepts. But every once in a while, we try to bring a real life situation in. And very often, the labels are forgotten. So I'm going to tell you that if you have a problem with a context and a label is necessary, I'm going to count the label as part of the problem. All right, guys. I know we covered a lot today. Thank you for listening, and I look forward to seeing you next time.